To the friends of courses in the cement industry, I hope to subscribe to the membership, so that we can continue to provide useful content. In this course we will detailed explanation. Dimensioning of tube mills. In this video we explain the components of the ball mill. Summary. The required driving power and the dimension of a tube mill can be calculated as a function of the mill output, the filling degree, the mill speed and the length to diameter ratio. The filling degree is defined as volume of grinding media expressed as a percentage of the total mill volume. The filling degree varies between 26% for air-swept mills and 33% for short mills. The mill speed is expressed as a percentage of the critical speed. The critical speed is attained when the centrifugal forces compels the outer layer of grinding media to rotate with the mill shell. A high percentage of the critical speed, approximately 74 to 75%, is generally required for a high filling degree and with mill liners without lifting effect. A low filling degree in conjunction with a lifting lining requires a mill speed of 70 to 76% of the critical speed. The length to diameter ratio of a tube mill depends on the grindability of material, fineness of product and mill type. The length to diameter ratio is within a range of 1.5 to 2.5 for raw mills, and 3 to 3.5 for cement mills. See this video about ball mill grinding process. Introduction. The design of tube mills is still a matter of experience. There is no complete analytical theory available that can allow optimal design of a tube mill. Many variables, such as length to diameter ratio of the mill, speed weight of ball charge, shape of liners, size of grinding media etc. and the material to be ground itself influence the output and fineness of the finished product. In this section it will be explained, main design criteria. 1. Filling degree. The filling degree is defined as the volume of grinding media charge expressed as a percentage of the total mill volume. The driving power is proportional to the weight of grinding media charge. The distance of the center of gravity will decrease with an increasing filling degree. The driving power has a maximum range of 40 to 45% of the filling degree. We follow together, filling degree. Shows in figure. The behavior of the grinding media charge in function of the filling degree, and the percentage of critical speed. We follow together, filling degree. Shows in figure. Today the following values are adopted for the filling degree of tube mills. We follow together, filling degree. Shows in figure. The filling degree in a tube mill can be practically determined by measuring the free height above the grinding charge according to figure. In this section it will be explained, main design criteria. 2. Mill speed. The operating speed of the mill can be expressed in the percentage of mill critical speed. Critical speed is attained when centrifugal force compels the outer layer of grinding media to rotate with the mill lining, or that speed of rotation at which the centrifugal power neutralizes the force of gravity, which influence the grinding balls. The grinding balls do not fall and therefore do not perform grinding work. This condition prevents continuous cascading of grinding media upon which effect grinding is dependent. We follow together, mill speed. How calculation critical speed for tube mill. See this example. The critical speed is obtained when the centrifugal force is equal the force of gravity. The critical angular speed will then be the critical mill speed can therefore be calculated as a function of the mill diameter. The operating mill speed is then calculated as where we follow together, mill speed. Shows in figure. The critical speed is obtained when the centrifugal force is equal the force of gravity. We follow together, mill speed. The critical speed chart in figure is based on the equations 1 and 2, and allows a quick determination of the critical speed for tube mills with various diameters. Depending on the application, normal operating speeds of tube mills in the cement industry, the range between 70% and 76% of the critical speed. Some the range was between 65% and 72%. We follow together, mill speed. The optimal speed depends mainly on the filling degree, size of grinding media and type of liners. Practical values for the percentage of critical speed are given in the following table. This table shows percentage of critical speed in function of filling degree and type of mill liner. In this section it will be explained main design criteria. 3. Length to diameter ratio. The length to diameter ratio of a tube mill depends on various factors. The most important ones are 1. Hourly throughput. 2. Hardness of the material, grindability, fineness of the finished product. 3. Open or closed circuit grinding. 4. Feed size. 5. Grinding system. On one side, the hourly throughput will certainly depend on the cross-section, and therefore on the mill diameter. On the other side, the material fineness at the mill outlet depends mainly on the retention time of the material in the mill. The main influencing factor on the retention time is the mill length. Therefore, the length to diameter ratio of a mill is an important factor for an optimal mill design. We follow together length to diameter ratio. The values of length to diameter ratio in the following table can be used as guidelines. In this section it will be explained main design criteria. 4. Length of compartments. With regard to different compartments length, the values in the following table apply to tube mills for dry and wet grinding. Some suppliers prefer to divide 3 compartment mills. South American Samoa approximately 30% of total length are for the first compartment and 20% for the second. In this section it will be explained weight of grinding media. The weight of grinding charge can be calculated as follows. Where we follow together weight of grinding media. The values for bulk densities of the grinding media are given in the following table. This table shows bulk weight of grinding media charge. In this section it will be explained driving power. The total driving power of a tube mill is the sum of the net power for maintaining the center of load gravity in a position of kinetic equilibrium, and power losses of friction and transmission. According to Mittag, distance B can be expressed as a function of mill diameter di, taking into account the following assumptions. 1. Distance B is always in the same relationship with mill diameter, same filling degree but different diameters. 2. For usual range of speed, distance B does depend on mill speed. We follow together driving power. The following formula can then be derived, where x is mainly a function of the filling degree and the size of grinding medial. The torque M can be expressed as, and the driving power N as a function of the angular speed and the torque, with the angular speed being the driving power N can finally be written as. We follow together driving power. For practical calculations the formula can be simplified to, where N equals driving power, Q equals grinding media charge, D I equals mill diameter inside liners. N equals mill speed. C equals power consumption factor, where power consumption factor, C equals. Formula, N equals. Allows the determination of the total driving power of a tube mill including all friction losses in the bearings, and transmission losses with an accuracy of 5 to 10%. We follow together, driving power. Formula driving power, N equals. Allows the determination of the total driving power of a tube mill including all friction losses in the bearings, and transmission losses with an accuracy of 5 to 10%. For multi-compartment mills, the total driving power can be calculated as the sum of the driving power of each individual compartment. The power consumption factor C depends on the filling degree, grinding media size and the value of X. Therefore, the value of C cannot be calculated theoretically. But by measuring the total driving power of industrial mills in operation, and by considering the known values of Q, Di, and N, the power consumption factor C can be determined. In the fig shows factor C versus filling degree F. We follow together, driving power. Formula driving power, N equals. Indicates that the driving power varies as the grinding media charge, which again varies as the square of the diameter Di, for a given shell length. That driving power likewise varies as the diameter, and speed which is an inverse function of the diameter, whence it follows that. This formula means that the driving power of tube mills of the same length, operating under the same relative conditions varies with 2.5, power of the internal diameter. Differences of length can be calculated by the following formula. By assuming the same ratio of length to diameter for both mills, the above formula can be written as. We follow together, driving power. It can be seen from the above that the diameter of a tube mill has a great influence, approximately d2.5, on the driving power. Whereas the length of the mill only has a linear influence. According to some authors, the amount of power a grinding mill can consume varies as a direct function of the length, and as a function of the 2.4 power of the internal diameter. The decrease from the theoretical 2.5 exponent probably results from energy released by the falling balls, when transferred back to the mill shell on its downgoing side. The capacity of the mill also varies directly as a function of the length, and as a function of the 2.6 power of the internal diameter. Fred C. Bond states that, theoretically the maximum exponent for size reduction entirely, by impact is 3. The difference between the two diameter exponents of 2.6, capacity, and 2.4, driving power is 0.2, and indicates theoretically a mechanical advantage of large diameter mills. The efficiency increases as the mill diameter to the 0.2 power, and the specific power consumption in kilowatt-hour per ton, required to grind should decrease in the same ratio. With the introduction of large grinding mills in the cement industry, the above-mentioned advantage was also expected. However, this presumed advantage in efficiency for large mills could never be proved. In the light of the present knowledge, no evident difference in efficiency between smaller and bigger mills exists. Thanks for following the channel, Courses in the Cement Industry. And please help us to continue and provide more information by subscribe to the membership and inviting your colleagues to watch this channel.